Okay, today I thought we'd have a look at one of the questions from the Pearson Module 2 review, and it's this question 27. Let's have a read of it together. We have a child of mass 34 kilograms dropping from a height of 3.5 meters above the surface of a trampoline. When the child lands on the trampoline, it stretches so that she is 50 centimeters below the initial level of the trampoline. Use g equals negative 9.8 meters per second squared. That should be squared there. So we've got the height above the trampoline, we have the mass of the child, we have the distance that the trampoline is depressed. Let's have a look at what the question is asking. A says, what is the spring constant of the trampoline? So that's the K in this work equation here. B says, at what point does the child have maximum kinetic energy? And C says, describe the energy transformations that occur as the child drops, bounces, and rebounds. So in part A, we've got a work formula. In part B, we're talking about kinetic energy. And in part C, we're talking about energy transfers and transformations. So we're going to be wanting to look at this scenario in terms of energy considerations. We're also going to be using an equation that we haven't seen before, and that's this work equation here. So this is an equation for work done on or by a spring. So that includes trampolines that has been compressed or stretched by a distance of x. And we have spring constant, which is just a measure of how strong the spring is. Okay, so this is an equation that we haven't seen before, and it's not something that we would be expected to remember, but it's something if we're given it in a question, we would be expected to be able to use. So let's have a look at this. I've broken this scenario down into three sort of time intervals for us. The first one is the first thing they tell us in the question, that we have a child that weighs 34 kilograms at a height of 3.5 meters above a trampoline. From there, they're going to start to fall towards a trampoline. They'll hit it, they'll depress it, and bounce back up. The question tells us after they've hit the trampoline, that they depress it to a distance of 0.5 meters. Right at this moment here, when they first touch the trampoline, this is another interesting point for us. So whenever we're looking at a question like this, we want to think about, where do interesting things happen? We usually consider the top and the bottom of an object's motion, but in a case like this, the time when the child first contacts the trampoline is also going to be an interesting time for us. So let's have a look at these three scenarios in terms of energy. Let's have a look at the top. We know that the total energy is going to be the potential energy plus the kinetic energy. Here we're at rest. Our velocity is 0. So that means our energy is just mgh, our gravitational potential energy, plus 0. But the question is, what is our h? There's a couple of things here. One is we don't know how tall a trampoline is, so if we wanted to measure it to the ground, we're going to have difficulty there. We could measure it to the height above the trampoline, but I'm going to pick a different reference level here to suit the question a little bit better. And we will come back to this in 1 second. Let's have a look here. Here where we've just touched the trampoline, again, our energy is going to be U plus K. We're going to have some kinetic energy, and depending where we put our reference level, we're going to have some potential energy too. But this energy at time 2, we know must be equal to our energy at time 1, because if we're ignoring air resistance, which we are in this question, there's been nothing else interacting with this child as it falls, and so the total energy must be the same. However, when we get to the bottom, we have something different. Normally, we're going to be relying on conservation of energy to answer questions like this. But in this case, conservation of energy is not held for just this child. The energy of the whole system is going to remain constant, but the energy of this child is going to change. Let's have a look at that. So the energy of this child is going to be the potential energy plus the kinetic energy. Again, here we're at rest. Right, our velocity is 0 right at the bottom of our motion, right? You can think of this maybe like almost like a yo-yo. As it hits the bottom, its velocity goes to 0. And what is our potential energy? Well, this is the lowest we ever go. So I'm going to set this line here as my reference level. Right, that's my h equal to 0 line. So that means our k is equal to 0. And because h equals to 0, u equals 0, and so our energy at this time 3 is also going to be 0 joules. Right, so we have lost energy as we get to the bottom here. Now that we know where our reference level is, we can work out our height up here. Our height is going to be 3.5 meters, which is how high we are above the trampoline, plus 0.5 meters, which is how high we are above that reference level, which is 4 meters. And so our energy here is going to be the mass, 34 kilograms, by acceleration due to gravity, 9.8 meters per second squared, by the height above reference level, which is 4 meters. And that's going to give us an energy of 1332.8 joules. That energy is going to be constant, so the energy here is also going to be 1332.8 joules. But the energy down the bottom here of the child is 0 joules. So then we have a change in energy. Our change in energy, remember, is going to be our final minus our initial, which in this case is 0 minus 1332.8, which is negative 1332.8 joules. We should immediately think when we see a change in energy that this is going to be equal to work done on the child, or work done by the child in this case. So the child is doing work on the springs, is stretching those springs out and converting its kinetic energy into the elastic potential energy of those springs. So let's have a look now and see if we can't answer part A. So part A says, what is the spring constant of the trampoline? And we're going to be using this formula given to us. Work equals half kx squared. And we know work is always going to be equal to a change in energy. So we get half kx squared equal to, and our change in energy is negative 1332.8. Let's quickly think about the sign here. This sign here tells us that the child has lost energy. Right? We are looking at the trampoline though, which this means that the trampoline has gained energy. So then we're going to treat this as positive delta E for the trampoline. Okay, so that gives us a half times by K times by X. Now, how far has the spring been stretched? So the spring has not been stretched 4 meters. It's not being stretched all the way down this thing. It's not being stretched at all. It's not stretched here at time 2, but it is stretched at time 3. And the distance it's been stretched is this 0.5 meters here. And so our X in this case is going to be 0.5. So this will be a half times K times 0.5 squared equals 1332.8 joules. So that is K by 0.125 is 1332.8. And so K is going to be equal to 10,662.4 newtons per meter. That's the units for our spring constant. And we're going to round that off to 10,000 newtons per meter because we only have one significant figure given in our question here in this 50 centimeters. So our answer should also be to one significant figure. Okay, part B says, at what point does a child have maximum kinetic energy? So let's think about what we know about the situation. We know that the child has maximum potential energy at the maximum height, right? That's just how gravitational potential energy works. Usually, we find that K is maximum at the lowest height. Is that true in this case? So let's think about this. Let us maybe draw a graph of the energy of this child over time. Let's have a look at the total energy of this child. The total energy of this child is going to be constant, and then quickly fall off to 0 as it hits the trampoline. So this is our total energy. And this point here is going to be where we strike the trampoline. That's where we hit the trampoline. What happens to our potential energy? Well, our potential energy starts off at a maximum and it goes to a minimum once we've hit the trampoline. It's going to fall off like a parabola, actually. That's just what happens to projectiles. So this is going to be our potential energy. And if we think about our kinetic energy wants to be increasing all the time as we're falling up to a maximum, and then that's just going to drop right off as well. Like that. So that's our kinetic energy there in blue. So this tells us that our maximum kinetic energy is actually going to be occurring right when we hit that trampoline. So we might phrase that as the child's kinetic energy is maximum as they first touch the trampoline. Beautiful. So ordinarily we see with a one of these energy time graphs that the kinetic energy and the potential energy just cross over. But in this case, because we have work being done on the trampoline, all of this energy goes down to zero as that trampoline gets compressed. Okay, let's have a look at part C. Part C is asking about the energy transformations that occur in this part of the in this interaction. So maybe let's try and just imagine, imagine in a video what happens to the child as they fall. So let's just draw the child here. So we have a child here who is up in the air, 3.5 meters. They are going to fall towards the trampoline, accelerating until they hit their maximum speed. Then the trampoline will flex and they will spring back up. So here at the top, they are at rest, but they have some gravitational potential energy. No energy in the trampoline at this stage. As they fall, that potential energy is getting converted into kinetic energy. And so the kinetic energy is going to increase, hit the trampoline, the kinetic energy is at a maximum. They are going to depress the trampoline and the kinetic energy decreases to zero in that time. Then that kinetic energy turns into elastic potential energy of the trampoline, which then gets converted right back into kinetic energy to push them back up. That kinetic energy, as they fly back up, gets transformed back into potential energy. As we're falling, we have gravitational potential energy getting transformed into kinetic energy. So this is normal with a falling object. We might want to be really clear though, and just identify that if there is drag from the air, that's also going to turn some of that gravitational potential energy into possibly thermal or sound energy as that rushes by the child. That child's kinetic energy, as it hits the trampoline, is going to be transformed into elastic potential energy. Elastic potential energy. And again, if we want to be really clear, we're probably going to be losing some of this energy because of the friction of the child's feet on the trampoline and the molecules of the springs alongside each other. We're going to lose some of this energy to thermal energy as well. Then the elastic potential energy, this is when the trampoline springs back. The elastic potential energy is going to get transformed back into some kinetic energy of the child. And again, we're going to be losing some energy here to friction. And that's likely going to be mostly thermal energy because of friction. And then lastly, as the child springs back up, that kinetic energy is going to get transformed back into gravitational potential energy. Okay, and again, we might want to add in here that drag is going to convert some of this energy to thermal and sound energy. Okay, wonderful.